everyone. As Annalise already stated, my name is Chrono, and I must apologize. I've managed to contract a cold just in time for this event, so if I have to sneeze or something, I'll turn away. Anyway, as she already said, I'm a student in the neuroscience program under the guidance of Doctors Lisa Ellis and Russ Costa, as well as the McNair Scholars Program. Excuse me. And tonight I'll be talking to you about a kind of technology known as brain-computer interfacing. Now, if you don't happen to study brains for a living, then you've probably never heard of what brain-computer interfacing is, or neural engineering, or anything like that. So neural engineering is an interdisciplinary science pulling from neuroscience, physics, mathematics, computer science, electrical and mechanical engineering, and so on, and seeks to create methods by which to interact with the brain, not just observe its mechanics. One of the more prominent goals in the field of neural engineering is to create brain-computer interfaces. Now, a brain-computer interface is a system that uses computers to communicate with the brain in some capacity. Neurological signals can be read by some manner of neural imaging technology and then used to operate a computer or robot. Or data about the world is in some way encoded into neurological information and then delivered to the brain via physical circuitry. Now, I want to elaborate a bit on neural imaging technology. We neuroscientists can't access the information stored in and in between brain cells, called neurons, so we have to implement one of several available imaging technologies to do what we want to do. The most common neural imaging technology in use today for brain-computer interfacing is the one you see on the screen there. This is an electroencephalogram, or EEG. This is the kind of device that we use here at Westminster in our neuroscience laboratory, so I'll be talking more about that one in a bit. Brain-computer interfaces come in two flavors, invasive and non-invasive. Currently, invasive technology is involved solely in the treatment of certain debilitating medical conditions, as it often requires brain surgery. A few examples are right here, the cochlear implant and the artificial retina. Both convert sensory stimuli into electrical impulses that can then be read by the brain. Besides these, such as robotic limbs and microchip implants sit directly on the outer layers of the brain are the current trend for this kind of invasive technology. The non-invasive type of brain-computer interface relies more on sophisticated algorithmic processing and computer technology in order to interpret fairly complex signals. EEG neural imaging technology tends to be prevalent for this kind of interface due to its comparative ease of use and low cost. The Berlin brain-computer interface, shown there on your left, allows an individual to operate a spelling program on a computer simply by imagining the movement of a hand. Interfaces have also been created to allow for robotic navigation, such as controlling the movements of a wheelchair by giving certain neural signals to the system. Recent developments, such as those at the University of Minnesota, shown there on your right, have allowed flying drones to be controlled by brain signals. Commercially available toys and applications have also come out in the last decade. One such example is the Neko Mimi accessory, which allows for the manipulation of a pair of robotic cat ears using brain signals. It's pretty fun, right? Other creations, like the Epoch interface, allow for interaction with custom-made computer applications and games. But a major limitation to using many of these devices, as well as some of the medical inventions that have been released, is that users must train themselves into producing the kind of neural signals that can be read by the associated computers as controls. This can be quite difficult to achieve and requires a lot of programming in order to correctly manage everything, with some neural interfaces requiring months of user training. In my opinion, that leaves a lot of room for improvement. This is where we come in. Now, we don't happen to have a neural engineering laboratory here at Westminster, but that won't stop us from thinking it's just as big as the researchers who have created all those nifty gadgets I just showed you. With the proper motivation and with the support of a very supportive faculty, even a student like me can think big enough to build a brain-computer interface here. And because the neuroscience professors here are just plain awesome, particularly in how much they empower students, we have officially begun work on the EggLink Project. With a working timeline of about 2 years and using EEG nets, artificial intelligence, a home-built supercomputer, and lots of sleepless nights, we're going to manufacture a system that will take any individual and allow them to operate a computer only using their eyes and fingers. This will be the non-invasive type of interface, as we're certainly not equipped for brain surgery here, and will implement computer learning algorithms so that the system adapts itself to the individual users, rather than requiring the users to train themselves to produce the correct brain activity for control signals. It will replace the normal computer interface devices, which are the mouse and keyboard, with brain-controlled versions of these items. The result would be quite user-friendly, and much simpler to learn to control than existing systems, all due to the implementation of artificial intelligence. It'll work like this. Continuous signals received from each of 128 electrodes affixed to the scalp will be interpreted in real time and then, and read by our artificial intelligence system to output into a set of predefined control signals that can be read by your favorite version of Windows, Mac OS, or whatever else you prefer. In this example, the eye movements of the user are dictating in what direction and how far to move the mouse cursor from a resting position. As Haley there looks to the right, the mouse cursor moves to the right. As she looks to the upper left, the cursor follows on screen. Here, the buttons you'd find on a regular mouse are mimicked by using finger movements, with a flick of the index finger acting as a normal left click, and a flick of the middle finger acting as a normal right click. A variety of distinct physical movements could be trained independently into the artificial intelligence component of the interface to allow for a versatile system of control. Now, I should note that while the system is oriented around actual physical movements, the target population of this research is individuals with injured, missing, or paralyzed limbs. It happens that the electrical activity in the human brain when attempting the motion of a limb is robust enough that pattern detection algorithms can parse out the desired information even in the absence of the limb itself, such that even amputees could use this system effectively. Treating such conditions as, say, acquired paralysis with brain-computer interfaces is one of the more prevalent goals that neural engineers are currently working on. Besides that, this line of research will open doors into future work on brain-computer interfaces at Westminster, with the outcome of future research aiding in the treatment of many debilitating medical conditions. And it's precisely that kind of demand for addressing the needs of the medical community that has fueled the research in neural engineering. Eventually, we may see that almost every physically limiting condition can be addressed by brain-computer interfaces. But besides just treating medical conditions, common technology can also draw from this field in order to achieve that same level of functionality. In the next few decades, we may see that many, many secrets of the brain will be unlocked. This will allow us to further master how to interface with the human brain, such that brain-computer interfacing may be the most common form of technology to which a person is ever exposed. Let me illustrate. With a show of hands, how many people here in the audience own a cell phone? Pretty good, right? Now, if I had asked that same question, say, 30 years ago, we might see maybe one hand, if that. Now, how many people here in the audience own a brain-computer interface? Not one. But I'll bet that in 30 years from now, if I ask that same question, we might see as many hands in the air as people who own cell phones now. I think that at the height of interfacing functionality, we may be able to see something a little bit like this. Ah, a lovely day at Westminster College. This scene is what a normal pair of eyes would see. But for those with a top-of-the-line neural interface, something a little bit more like this is what your brain would see. Now, this simple example is contrived, of course, but the functionality of modern mobile computing, such as smartphones, could be overlaid directly into the nervous system. Here, a friendly menu offers the current weather conditions, because obviously you can't tell by standing outside, a health monitor connected to the heart and other organs, and route planning to the nearest shot of caffeine. A simple neural click of the desired menu item, and off we go, following the directed path to Griff's Roost. Now, something like this, involving fully functional, non-invasive interfacing with the senses, may not be on the table in our lifetimes. However, if I have anything to say about it, we'll see something like this sooner than later. But for now, neural engineering faces three main challenges to overcome. Because every brain is different, continuing research into artificial intelligence is key to the functionality of neural interfaces. Besides this, consideration must be given to invasive versus non-invasive technology. I don't think that anyone wants to go through brain surgery just to have a map to the coffee shop implanted into their vision, in my opinion. Lastly, the traditionally isolated disciplines of the hard sciences won't be enough to solve the engineering challenges that await us. Many experts from different fields will need to come together in very creative ways to solve some very tall hurdles. With our EggLink project, we're attempting to address all three of these to the fullest extent possible. That said, in the future, the fullest extent possible will be pretty amazing, I think, and neural interfacing will be able to change our lives in many delightful ways. So with that, I thank you for listening to my presentation. Please enjoy the rest of your evening with my compliments.